are two different interfaces, right? One for the native SVM kind of use cases for normal, user space DMA, and we have a separate mediated device or a sub-device framework for exposing devices to guest operating systems. And rather than having two, I think the idea was, can we just converge on one? And I think one other idea that's kind of propping up is saying, why can't we just add more bells and whistles to the user space DMA framework and make that somehow fit all the needs that we need for a guest usage, right? So at least at the end of the discussion, I have one primary thing. We need to know what to do. How do we proceed for device models that we are currently in progress? And clearly, coming up with a new framework might be a multi-year effort. So clearly, that's not something we can solve in the next month or 2 months or something. So given that we have devices that are coming in and we have made this choice with using Vfio, what is our short-term goal? And maybe this is a good segue to find out, like at the end of it, say how do we want to actually keep moving, or changing the standard of not using Vfio, but is it something else actually, right? And that needs to be kind of looked up. This is a presentation we just kind of put together to show what the differences are between each of those different approaches. And Vfio PCI, everybody is well aware of, where we just expose a full PCI device to guest user space. No changes there. We consciously chose using MDEV also being exposed through Vfio. Primarily because that infrastructure in the user space is already well bolted and well understood, and it had all the good ingredients that we need for exposing things to user space. So we didn't really need to actually find any new frameworks or something like that. So Vfio was just good enough for those, right? And I think the primary concern is doing device simulation. Is it acceptable? Does it introduce? Will people start abusing it? Right, in terms of trying to use it for the wrong reasons or whatever it is, and that needs to be audited, right? So, and I think Kevin has some suggestions towards the end on if that's a concern, how do we move forward, given Vfio PCI is the de facto framework that most device simulations actually use today, and it brings all the good things about using migration support. It already wraps in any of the PCI device stuff. Like we can expose it as an MSI for user space, and even though internally it is a different storage concept for interrupts. So it kind of has all the good nuts, bolts actually that are required to hide and give a consistent user interface, right? And that's the primary focus. And on this slide, I have how the user space API is. And currently, we have SVM usages where we have apps that are using directly the user space framework for trying to get a path to the hardware, and they just submit work and it's all done. But if we want to actually move that same framework and leverage and extend it for using exposing devices to a guest, there are additional changes, right? In the sense that every sub-device framework needs to have changes both in the host kernel. They also need to have changes in QEMU for supporting those usage models. And there is obviously a guest driver, as always, right? So this just kind of changes how the user interface is going to look like, and we pretty much need to reinvent everything that Vfio has already offered in terms of a device interface. So although it definitely looks like a possibility that we could switch from Vfio to the other model, it is sort of constraining in the sense that there's a lot of new functionalities we would need to add and reinvent and do the same things that Vfio has already done actually for the user space framework. So that's the caveat. So if Vfio is not it, right, then we need to make a decision on how do we move longer term over a new framework and what that is, right? So, and that's where we can probably focus after the micro conference. But at least for now, we would like to know, given that we made a good choice a while ago, and where we are today, what is the consensus on moving forward in the short term, and what are our goals trying to reinvent this framework and revitalize this with a new framework or new interface, using the current user space DMA API extension. That's something that I think we need to actually solve maybe after. But for the short term, we need to figure out what the right device model is for exposing things to user space, especially for guest control. Right. That's the idea. And I think the proposal is, at least from what we have done so far, Vfio mediated devices has a good merit, which is obviously why we made a choice a couple of years ago. And I think when like Jason and others pointed out, it's possible that people might abuse it for the wrong reasons. But I think some of the suggestions that Kevin had was, maybe we can have like a voting process, because usually the device drivers themselves don't go through a good audit as much as what the Vfio thing does. So we need to figure out a way on how to control and merge those drivers and make sure that the purpose is right for the usage, right? That's the thing. And obviously we can look at certain aspects, for example, PCI configuration, emulation, and things like that. We can certainly move into user space, or we can consolidate that framework in the kernel itself, rather than every device-specific host driver to actually supplement that functionality. So those are small, improvements in reducing code duplication and things like that. We can definitely focus on keeping Vfio as the primary model. So that's pretty much what I had in the slide deck, and we have a few backups just as resources on showing the history of how the mediated driver framework came up for the scalable IOV project for Intel, and we've been discussing this with at least with Alex and folks for a couple of years now. So I know that there's been another proposal, but we would like to see what is our what is our goal going forward in the short term at the moment. So I would like to open it up for discussions, at least maybe get a few words from Alex. And I don't know if I can see Jason too. So so Jason or Alex, if you guys have any thoughts on how to move forward with the mediated driver framework, we would love to hear that.
So my impression is that I largely support this effort, and I kind of consider it the vendor driver's choice of whether they're willing to take on some of this increased attack surface and extra bloat. Our only really control point of being able to determine what's the right amount of emulation to have in the kernel is whether or not it gets accepted upstream, because these interfaces are exported, and we do have out-of-tree drivers. Both NVIDIA and Mellanox have drivers, and maybe others, I don't know. So we really can't control what out-of-tree drivers do, but we can look at what we're willing to accept into the kernel. And there certainly is a risk that somebody would want to avoid all the hassle of getting a driver into QEMU and just write some out-of-tree driver and make use of this interface to simplify their work. So there's two sides to that coin of enabling the whole virtualization stack. It makes it really easy, but the kernel is not always the right place to do that. So I'm sure Jason has some comments.
Well, I'm just worried that this Vfio MDiv is really becoming a new driver model. Like we saw that with the VDPA discussion, where the initial impetus was to create a whole subsystem and hide it under MDevs, basically ignoring the driver model we have in the kernel for no reason other than what has been presented here is we want to plug it into QEMU. So the only way to plug it into QEMU is to use VFIO MDev. And as long as that's the kernel thinking, so the only way to plug into QEMU is to use VFIO MDev, there's going to be a lot of these drivers. And I don't know if that's really a good thing, especially when we have two versions of every driver now. We're going to have the user space version and the VFIO MDev version. The VFIO MDev version is only used for virtualization. And now we have to do security audits of both of these things. The vendor has to maintain both of these things. It seems like a very small win in the long run just to plug it into QEMU without having to do a little bit of user space work.
If we don't do the... Go ahead,
Alex. No, go ahead.
If we don't do the VFIO route, aren't we just going to end up with a lot of different vendor-specific user interfaces?
We already have that. IDXD already provides a vendor-specific user interface. It just doesn't have the tiny bit extra to do what VFIO MDev offers. And I think the problem here is that in the kernel, VFIO MDev, or VFIO in general, has got a monopoly on all of the things required for virtualization. So if you want to pass through interrupts with VTD, or you want to set up a VIOMMU, you are stuck. You absolutely have to use VFIO. Even though you already have a user space interface that's vendor specific or driver or device specific, or maybe you've already have a UXL framework or RDMA or one of these other things, you are stuck. You have to go back and you have to create a VFIO MDev driver to utilize your device in virtualization.
Yeah, I think that the difference is, Jason, that user space needs are significantly different from what you need for virtualization. Like the ones you mentioned, right? We need to support posted interrupts. We need to actually support, for migration. Like, how do we make sure that that when you want to prepare for migration, every device driver that in the user space also needs to participate and develop the same things rather than having a consolidated VFIO interface. And it's not necessarily that everything needs to go through VFIO, like you say. Like if there is another alternate that somebody is willing to come up with, obviously, but this one doesn't seem to actually remove any of the bottlenecks, because you're going to have in QEMU, you need a VDEV extension for the user space component anyway. The user space that we use for user space DMA is really, really small compared to how much bolts you need to add on to make it fit virtualization needs, right? It's not a small amount, because you like, for example, we need hardware, normal hardware control. The other way we have looked at it, like for instance, we had a small effort to say, hey, can we make VFIO less loady for user space? For instance, can I have a VFIO Lite? All I really need is to bind MM or whatever it is. If we can extend VFIO to provide the minimum functionality that's needed for user space, can we then make that as the unified user space interface, even for SVM, compared to completely going a separate route for each driver? We have done that also, actually.
I know.
There are good reasons we didn't do that.
We've looked at that too, and it's not a good idea. There's a lot of reasons why you don't want to do that, and I think those are the same kind of reasons why you don't want to have VFIO be the only single way to do virtualization. And I'm not entirely convinced it's all that different. So let me ask you a question. How do you plan to do migration with VFIO MDev in the picture? You have to serialize your hardware state somehow in a device-specific way. So we're going to grow a whole bunch of device-specific VFIO MDev ioctls to do migration now, and then again come back to having a whole bunch of user space to support that?
We've already accepted a set of UAPI interface for doing migration that exposes a region that has some registers in it that control the device state and allow a protocol for reading and restoring the device state.
But nevertheless, I think our lieutenant just flashed a 5-minute warning, actually. So I'm just saying, like, we have something that we need today, right? Versus another one looks like a possibility. So we do things because we have a real need for it. And what I'm saying is that if you need to extend the user space DMA to fit the virtualization needs, that would be a separate effort. We don't need to stall what we are doing now. Would you agree with that, Jason? Right. We don't need, I'm just saying, like, do we put brakes on everything that we're doing and say, let's do a multi-year effort trying to actually figure out like how to fit
this? So first of all, I think you're really over broadening how much effort it is to make the two small changes to the user space. But I don't know. Corlina came on. We should let her talk.
Yeah, one thing I think we should also consider is to avoid fragmentation. If I look at the currently upstream MDEV drivers, 2 of them are SV90, and there's just no question that they will use anything like user space DMA due to the way SV90 devices are set up. So if there are more virtualization devices coming in through user space DMA, we'll have suddenly one set of devices that need to be managed via Vfio means and other devices that need to be managed via other means. And for Vfio MDEV, we already have, for example, MDEV control to just configure the devices. And any user space program like management program like the Word would need to suddenly support 2 sets of APIs to manage devices, and I don't think that's a good idea.
The management problem is a big problem in general. Like we've been dealing with very simple devices so far, like IDXD is actually quite simple, but when you start to talk about things like networking devices, creating an MDEV for networking devices, connecting it up to switch dev, managing the switching plane, the control plane for that is actually extremely complicated. And we've been looking at using MDEV as well for that flow, and it's kind of sketchy. It's not very good. So we're looking. I'm more or less expecting that we're going to have 2 control planes, at least for net. We'll have one that's based on DevLink that can hook up to switch dev, and if an MDEV comes out of that as a side effect, then that's kind of how it will be.
I think we have only 2 more minutes, but I think we need a forward path actually. Like I said, now, and there's nothing stopping the user space framework to actually grow into something where VFIO is. But I don't think we would need to break what current effort is, because the other part is unknown still. I think Jason characterizes it like it's a really small tool. It's a very small effort, but it hasn't been done. And at least, given what we have done so far, it doesn't look like a very, very small effort or a trivial effort. That's my read of it. And definitely if Jason has a hardware piece that you need to migrate and show it as an example, and definitely, hey, that's perfect. Now everybody can adopt and grow with it. I just don't find that we need to actually stop what we are doing now, because the other part is still unknown in our mind, right? So it's something that we have not done yet, and that somebody needs to do to make sure that it is, yes, this is definitely a very, very small effort. And until that is done, I don't know what to do, actually.
It's usually how we get work done in the kernel, right, is by saying this is kind of the architecture the kernel wants to be, and then people actually have to sign up to do the work. And I think if we keep going ahead with MDEV, it'll just never be done. Everything will be an MDEV. And that's kind of the decision point.
But somebody needs to break the norm, right? Somebody needs to break the norm and say, like, yeah, I need to do something different, because this is what I would like to do. And rather than that, and that needs to be experimental version, right? When we just certainly can't say, like, no, we don't want to do anything with the MDEV, because there looks like another idea that might be promising, but somebody needs to take that effort and do it first to prove that this is good enough.
So let's give Jerry and Alex a talk.
Sure.
Before we're done here, because I think we're done. Jerry?
Mute.
I don't have anything at the moment.
Oh, okay. Alex, do you want a final word?
It seems like we're still have things to hash out. Should we schedule a BOF?
I think that'll be a good one.
Okay.
I think that's good. Yeah.
Is everybody available for the evening session of BOFs tonight, or should we do it Thursday or Friday?
Know the time? Sorry. Why don't we coordinate in the chat?
Okay, sounds good.
All right.
Yeah.
Thanks, Alex.
Thank you very much. Sorry, guys, for interrupting you. You're a presenter, so the floor is yours. Thank you very much.
Okay, thank you. First, sorry to interrupt you at work. Yeah. So, yeah, this is.
Sorry, you're very quiet.
How about now? How about now?
No better for me.
Still quiet. Please speak close to the mic.
Yeah, move closer to the mic.
Okay. So how about now? Closer, I think. Hello?
Oh, no better.
Oh,
Could it be wrong microphone?
how about now?
No change.
How about now?
Nope, still the same.
For the same?
Yeah.
Yeah. I'm using the computer mic, so yeah.
Shall
Please, in the interest of time, go ahead. I mean,
Okay. Yeah. So this is a co-work from me and Jacob. So this is about the enhancement to IMU and Vfio use APIs for guest SVA. So first, I'd like to have a quick recap about guest SVA. So how the diagram shows, we have uh, four major flows across guest virtual MU and QMU virtual MU emulator and also VFIO and kernel IMU driver. So we have multiple interactions between the user space and the kernel space since the virtual MU located in the user space. Because of that, we have new user APIs introduced for guest SVA to VFIO. And also, we have a Iommu UAPI to define the data structures used to interact between user space and the kernel for guest SVA setup. Okay, so next one is the IMU UAPI data structure was merged early in 5.3. It includes the data structures used by SVA, and the data structure is conveyed by VFIO user interface. Um, in the past several months, we have some enhancement to the IMU API since we wanted to address flexible future extension. And also we define the roles between the IMU and the VFIO. Like VFIO handles its own data and pass its user pointer to IMU core. And the IMU core will do the data copy and then go into vendor IMU driver. And we also have some sanity check on the user IMU UAPI data based on the archetype and the flex in the IMU core. And also we added a new UAPI to report the domain nesting info, which is new compared with the previous version. This API aims to report the nesting and cap informations like the supported past bees and the way to set up nest translation and other related capabilities. Also, in the enhancement, we also have the documentate the IMU UAPI design and provide examples for the interactions with the VFIO. Okay, so for the VFIO enhancements, I didn't have at least separate slide to list the enhancements, since the enhancements is straightforward and based on the previous chart. To each flow will have an extension to VFIO. but there is some different difference between the platforms. Like for Intel platform, besides the major for extensions, we also have the passive allocation and the free interface for Intel platform to explicit allocate the passive from host side. Okay, so next, I'd like to share about the SVA upstream plan and also the status in community. So we have three phases. The first one is the PCI device without page fault. The second is the page request service. And the third is the mediated device support. So we are currently working on the first and the first phase and the second one. The green part is what we have already merged, like the initial IMU UAPI, which is in 5.3, and also the IMU driver extension to support gas SVA, which includes the bind and bind gas page passive and caching validation. And this is already merged, and also we have the IMU driver PRQ reporting merged, and we also have something still in under review, like the user API enhancement and the IOASID extension for gas SVA, and also the Vfio gas SVA extension. And but we also have something not out yet due to the dependence, like the Vfio gas, the PRQ support, and also the IMU driver support for mediated device on the fault reporting and the response. So this is the overall status about the upstream, and actually something like the IMU user API enhancement is in version 7, and we are seeking if we have a chance to make it mergeable or accepted by I think this is one is by IMU in IMU side, so maybe need some help to get it merged or so. Yeah, and but of course, if there is a still gap, we must still make effort to move it forward. Okay, so I think this is yeah. I also have there a list to show the patches under review and the link. So I need you guys to help, to have your comments and to make them merged for mergeable quality. Yeah. So I think that is all for my presentation part. Yeah, my major purpose is to to have your help for review and feedback. Yeah.
Is there anything specific you're looking feedback on today? I mean, if you can be more explicit, maybe someone in the room can try to comment on it.
Okay. I think for IMU user API enhancement, I guess maybe Alex and also York, you guys own the own the control, yeah, to give your final decision on it, yeah. And for Vfio, it's naturally Alex control on it. And for IOASID, I think Yong and Eric, yeah, and Jacob, yeah, will on their progress. Yeah.
So I think Jacob's latest series is I think we're running out of comments on it. So it seems like it's about time to be accepted. That would go through York's tree though. So maybe looking for York's input on that now. And then the VFIO changes are of course dependent on those. So we need to get agreement on getting that into the tree before we can accept the VFIO extensions.
Okay. Yeah, that makes sense. Yeah.
Yeah, so if there are enough review buys and egg buys on the patch set, I can take it. I haven't had the time to review it in depth myself, so I'm relying on the reviews here and to see if everyone is happy with it. So that's the acceptance criteria for me.
Okay. Yeah.
Yeah, I just need to do one more update. Some minor comments from Eric also. So I'll send out the V8 and also rebase.
Okay. Yeah. Okay. I will also prepare version 7 if you have your version 8. Yeah.
Sounds good.
And for the QEMU patch, I guess I'm not sure if we have Peter Xu in the code, but I think I guess Peter Xu may have much more review comments on it, and also Eric. I think Eric's work dual stage SMU also shares some common code with me. Yeah. I think that's all. Or from you guys.
Yeah, just a comment, Eric speaking. So I intend to review the QEMU series, so I will spend cycles on it.
Okay, yeah. Thank you very much, for your comments in my previous versions. Yeah.
Okay.
Okay, so
Anything else? I mean, you just have 5 minutes to the end of the session. I don't know if you want to ask anything else, because I mean, we'll keep it to the scheduled time. So feel free to use your time as you need it.
okay, I guess I have showed my what I wanted to show here. Yeah. But I'm not sure if any other viewers has something want to discuss directly. Yeah, there is any, maybe we can talk. Take the 5 minutes. Yeah. If no, I think maybe I can just give out the 5 minutes to other people. Yeah.
It looks like you're done. I think we'll take 5 minutes to switch over to Jakob, and because I mean we need to keep in sync with the schedule for the live stream. So I think people can get 5 minutes of their time, and we'll restart in 5 minutes with the Jakob session. Thank you very much.
Yeah. Sure.
So should I start now?
Wait till 40 minutes past the hour so that you're in sync with the schedule. Thanks.
Okay, thank you.
Lorenzo must be having some military background, I think.
I'm doing what I'm told.
I just thought I need to make that though. We have a few free minutes, so.
I was hoping to steal some time from E.
Yeah, I'm sure you know the war is but yeah, finally it gets it done.
Maybe this will help. Jacob, you can go ahead. Thank you.
Thank you, Lorenzo. Hi, everyone. My name is Jacob Peng. And E and I both work for Intel. We work on the shared virtual memory in the past maybe 3 years now. So today we're going to talk about the IOASID extensions, which is proposed. We sent out a patch version 2 last week, and we want to use this time slot to ratify the design of this API extensions and get more feedback, and also kind of lay out the problem statements in more detail, because we have this extension is largely driven by the Intel scalable IOV usages for SVM mostly, but also guest IOV as well. Just a little background, IOASID is kind of a generic term for PCI packet and ARM's substream ID. So it's basically just a 20-bit number, but it quickly evolved into something more complicated than that. So here is the problem statement. When we enable guest SVA support, we realize there are gaps for exist for the IOASID code that we merged since version 5.5. So in this slide, the color green represents the existing features that's in the main line, and the color red is the ones that's the topic we'll discuss, and that's the extension we're adding to support guest SVA. So as it is today, IOASID provides basic services, allocate free lookup private data, and also provide a custom option for customized allocator. It can be used for VTD's virtual command interface in the guest. It also has a kind of loosely defined IOASID set concept. Basically, it's a token that can be passed into the IOASID allocation function. So IOASID allocated with the same token can be deemed as under the same set. So we can use that for some basic like ownership permission checking. But as we grow into supporting guest SVM, realize we also want to add more things. Those are, so number 4 is that we want to add more kind of group management APIs, so that IOASID assigned to guests can be managed for quota enforcement, permission checking, also notification within the group. And IOASID is widely used inside kernel by many components. So many users, when IOASID changes states or being terminated, we want to be able to synchronize with all the users. So we need some synchronization mechanism. And in the guest use, in order to support like migration, the guest may have its own namespace. So we want to support the mapping between the guest packet and the host packet. And then finally, because of the multiple users, we wanted, and each user may have its own hardware context associated with the packet. When we terminate the life cycle of the packet, we want to make sure we don't cross the lifetime before it gets reassigned, reallocated. This is just a graphical view of the IOASID set concept. We're proposing basically, in this case, we have two guests, VM1 and VM2. They are different sizes in the graph because they may have more, VM1 may have more assigned devices, therefore needs more passets, because passets is a limited system-wide resource coming from the same pool. But each guest passet has to have or IOASID has a physical IOASID backing in the host, so it has to be mapped to a host passet. But they don't have to be identical. In this case, VM1 and VM2 both have guest passet 1, but mapped to different host passets. So we could have multiple passets. That's sorry, I'm using passet and IOASID interchangeably in this context because that's what VTD is using. So we want to have VM1 has its own IOASID set, and VM2 has its own. So within the set we have a guest and the host packet mapping. IOASID set is not a pure, IOASID or packet is not a pure software construct. It's not like a PID, it's just a number, but it has, in this case, Intel's IOP platform. Packet has hardware context in almost all of the series except Vfio. So it can packet is one single packet can be used by CPU, so the packet MSR, IOMMU has the PASID table. KVM has a PASID translation table. It does the guest host translation. And the device drivers program PASID into their through descriptors or the queue. So all of these users using PASID, and the VFO, of course, is the interface to the user space and to the guest. So PASID gets allocated and free, and also state change through bind interface. And the users, some of the users like KVM only listen to the events. They don't need to publish anything. But IOMMU, for example, when it's done bind on bind, it's need to publish its status to the rest so that the device drivers or KVM can know the PASID is being established. So one of the challenges is that we want to make sure all the PASID users are in sync. And also when the PASID terminates, we want to stop DMA and stop the translation. And also, whenever necessary, to invalidate the hardware cache and also drain PASID in the device. So all these things needs kind of a publisher and a subscriber pattern, and then we're thinking to extend that with a notification mechanism. So we'll talk more about the proposed the solutions. So first, we want to redefine the PASID, the IOASID set concept from basically kind of promote that from a simple token into a group of PASID concept, and also change the allocation flow. So currently, we just go allocate PASID with the token, and now we want to change it to do allocated set first, and then allocate PASID within the set. This way, the ownership is set, and the quota is managed. And also, we want to add notification mechanism that include both a global notifier and also per IOASID set notifier. That's for the users such as KVM that only cares about the PASID that's allocated within the set, within the VM. So this is more efficient. We also want to add graph counting for the PASID so that PASID is not reallocated until the last reference is dropped by the user, but last user. This way, we don't cross life cycles. In order to support the guest and the host PASID mapping, non-identity mapping, we want to add a so-called PASID set private IDs. That's just a generic term for guest PASID. So those are the proposals in this patch set. So I got some reviews from Baolu and John Philip. So I would encourage people to give more feedback. And it's still in its early stage, but also write a kernel doc to try to explain the flow. So this is a kind of a diagram showing the interactions of PASID and its users. This is mostly based on the scalable IOV framework. So in the center is the IOASID. It has multiple sets. In this example, we have 2 VMs, and when the PASID starts, the life cycle is being allocated through the guest virtual command interface, and then down to the allocated free through Vfio newly extended API. Once it's allocated, it can be bind to a guest page table, and that's the bind call also goes through Vfio and then down to Iommu. The Iommu driver performs the bind and then store the guest CR3 into the passive table entry. And the IOMU driver will send out a notification, say this passive set is bound, and then KVM will get notified and then update its passive translation table, and the guest can start using the passive for work submission. In this case, is for unqueue command. And similarly for media device drivers, and they're also listening to the passive state change. For example, when a passive is freed, the device driver needs to drain the passive and stop, of course, stop DMA. The reason why we need the notification for guest SVM is that the order the request come from user, so we cannot, unlike the native use, the bare metal use, we cannot enforce order. Like we could have a free call come before the unbind. So we need to deal with all this situation where the bare metal case we can pretty much keep everything in order by just calling drivers. The next 3 slides are just details of the API prototypes. Not all of them, but the key ones we introduced: the set API, notification APIs, and the private IDs. So I just for this time, I would like to get more feedback on basically the design, especially the IOASID set kind of API groups that deal with the 3 challenges we're having: the state synchronization, reference counting, and a private ID.
Hey Jacob, so I have a question. So why does the mapping between guest and host IOASIDs need to happen in the IOASID core? I think this is more a task for the virtual IOMMU implementation, right?
Yeah, it's the virtual IOMMU performs basically catch the the passive allocation, but when the guest use the guest could use physical IOMMU, but for like a physical passive, but for live migration, it's better not to tie guest passive with a host resource. So we have this passive translation done in the hardware, and so
you have a guest to host IOASID translation in hardware.
Yeah, microcode.
Okay.
And also when the guest program guest passive into the device, we will say MDAP, and the device driver need to do a lookup, see what is my physical passive. So that provides IOASID could provide this kind of service lookup.
So why does how get the host notified when the guest turns down an IOASID? So it deallocates it on the guest side, and how does the host get notified about that?
Sorry, I didn't get the point.
So the guest can allocate guest pass IDs on its own, right?
Yeah.
So and in hardware you manage a table between guest pass IDs and host pass IDs. And now when the guest stops using a pass ID, the host needs to know, right? Because it needs to tear down that guest to host mapping somehow. So how does that work?
Yeah, so when the guest tear down the guest passive in the virtual IOMMU's passive table, and then when it flush the passive table cache, that's where QEMU gets notified and then pass down the passive cache invalidation to the host, and then the host knows this passive is gone.
Okay, and then when QEMU gets notified, it can do everything to tear down the host pass ID, right?
Yeah.
Okay, so and where do the notifications come into the picture? You were talking about notifications.
Yeah, the notification is when things are kind of out of order. So because the IOASID allocation free is a separate interface than invalidation, also bind unbind. So I don't know, a malicious guest or some misbehaving guest could do a free directly calling the Vfio interface. And in that case, the path is still bound to a guest page table. And we want to be able to capture that and then send it to the user, at least clean up all the context. So the notification is for more for out of order situation.
Mm.
In the host bare metal, we don't need notification.
But in a guest, every PES ID associated page table is translated again by the guest physical to host physical IOMMU page table, right? So don't see how the guest can do something malicious except to its own. Did I explain that, please? So the guest can only host itself, right?
Yes. But from API design perspective, we want to be more robust in the host. So, and also IOASID is kind of a separate subsystem than Vfio. So we want to be able to. There are also potential in-kernel use case we need a notification because in general we have maybe multiple publishers of the IOASID state change. And we want to be more kind of resilient and self-contained. You're not counting on certain guest behavior. So having a notification can enforce the users to clean up. And another reason is also we need a kind of order the notification. Since the teardown has to happen in order. For example, we want to stop the CPU submitting work first, and then IOMMU or the device driver. IOMMU driver can go last because it's more fault tolerant. Sorry, does it answer your question?
Not entirely, but I'm not sure I understand the whole picture yet. So
yeah, maybe we need a breakout session after this. We can maybe use one of the hack room.
Yeah, that would be great.
Yeah, I would also love to have Jean-Philippe's feedback. Okay, we can coordinate on the chat. We're going to run out of time. Thank you, everyone.
Thank you.
Thank you.
Thank you, Jacob. And I think, well, yes, sure, please coordinate. Well, the hack rooms are there to be used anyway. So I think at least you explain the issue and let's coordinate between us to discuss it further and bring it to completion. So thank you very much. And I think now we have a short break and we'll restart at 15 minutes past the hour. So thank you very much and see you in a short while.
So, Lawrence, let me know when it is. Could you start?
Yeah, let's give people some time. I mean, just a minute or so, and then should be able to restart. So we are about to restart. I mean, the floor is yours, Rajat. Feel free to go anytime you wish. Thank you very much.
Sure. Thank you. Hi, my name is Rajat, and I'll be discussing the external untrusted device management today. So the goal here is to present some problems and some approaches I tried and some challenges I faced and get some feedback on the approaches and the challenges and some suggestions to overcome those challenges. And of course, and to make some proposals along the way. Okay, let's start. So just wanted to set the context here. What currently happens in the kernel? So the firmware marks certain ports as external facing. This is available today both for device tree as well as for ACPI. And PCI marks any devices downstream those as untrusted. There's a flag in PCI device that we use. And that untrusted flag is then used to do different things. PCI Iommu drivers use it, at least the Intel Iommu driver uses it to impose strictness, to also set up bounce buffers. And PCI uses it to disallow the address translation. So essentially, there are different uses for it. So one of the cases, some of the cases that are not covered today are like today the trust is tied to location. So what firmware tells us is that these are external facing ports. We use it to populate a field called untrusted. So there can be internal untrusted devices which cannot be specified today. And today that property rests at the root port level. So we can only we can only mark the hierarchy starting at root port as untrusted. So if there is a PCI switch in the system, there is and there is no way to mark certain devices as untrusted. So essentially, there is a way. We need a way to mark devices as untrusted independent of location. That could come from user, that is command line or sysfs, or it could come from platform. The problem with coming from user space is like sysfs is only available after boot. So any devices that are in the boot path and they cannot wait. So we cannot use sysfs method to get these to get location or untrusted information from the user space. Platform is a more appropriate choice. So I'm posing that we add a new property that allows us to, or we support a new property that allows us to pass this information to kernel from device tree or from UAPI that certain devices are untrusted. So in my opinion, we should have two separate fields, location and untrusted. Location is something we already get from the firmware today. Untrusted is something we do not. Kernel components can continue to use them as needed. I had long discussions over upstream mailing lists, and I believe the discussion there was that it makes sense to have these in the device core versus PCI. So I've tried to break down my proposal into 3 RFCs, but it's mostly from the it's mostly to kind of make it tractable and make it in phases, because make it tractable and make it in phases. So, oh, sorry, I just noticed my camera was not visible. Okay. So what is location? Location is an immutable property of the device. And in the context of this discussion, our primary interest is in defining it internal versus external, that is within the boundary of the system. And currently, we already have this information from firmware, so it's easy to expose it to user space. There are use cases for it in user space. For example, we may user space wants to do some statistics collections for the device. It wants to show something in the UI when an external device is connected, or some other logging or whatever. So the key point here is like, how do we initialize this location? We initialize challenges. So I've kept that discussion of how can we override using SysFS to the RFC3, which is in 2 slides after this. But it has challenges. The primary challenge being that this information is needed really early. And for boot devices, for devices in the boot path, the SysFS approach might not work. The second field is the untrusted that I talk about. So essentially, it represents a knob that defines trustworthiness of the device. And again, initialization options are similar. So today we initialize it from location. So if we don't, so we can continue to do that today, but additionally also introduce a property so that firmware can mark devices as trusted or untrusted. And then we can provide options to override it by the user. Yes, Bjorn?
Sorry, I don't know if you want to hold questions till the end. That's fine.
No, I think it's okay too.
So I'm still a little bit uncomfortable with this untrusted idea, because it seems like that's more a property of the driver than the property of the hardware device itself. So when you're talking about an internal device that you want to be untrusted, I'm not quite comfortable yet with associating that with a device.
So essentially, even today, like what we have is like we have the untrust at the device level. That flag today is at the device level. And Oliver Upstream, I think, chimed in. He said he had certain devices. I think he called them, I don't know what devices they were, BME or something. He mentioned
it's BMC devices. So the baseboard management controllers, essentially the little computer that boots your big computer. So they're generally attached to the host using a PCIe interface, and they do allow you to do things like spoofing the vendor and device IDs. So in theory, you could make an arbitrary driver bind to your BMC's provided PCI device. So in that case, I would not want to make that a trusted device. And if I can do something on the host to prevent that device from being used, that'd be good.
So essentially, I'm not proposing anything new or groundbreaking here. All I'm saying is instead of populating trust from a location, we add a new property that tells the kernel that firmware wants to, or the platform wants to treat this as untrusted, and of course make it configurable in user space. User space can override it.
Isn't the problem that it's not the driver that's trusted or untrusted? It's only if you've got a device on the other side that has direct access to the DMA, right? That's what's untrusted. So if you've got like a PCIe device plugged in, that's the untrusted thing. It's not the PCIe driver in Linux or the endpoint driver.
So essentially, there are both the schools of thought, and even like within Google, there is like we are trying to build an allow list of drivers. But essentially, from a kernel standpoint, I think the feedback I got was that this should be a device level property. And if you want to untrust drivers, or if you want to keep it at a driver level, it should be part of the user space. So the user space, so you should build a mechanism using which the user space can choose to allow or deny certain drivers, and that you should try to build infrastructure in kernel that allows you to do that.
So is
right.
the trust?
Go ahead.
If we learn about trustedness from the platform, are we confident that that property is the same for all possible OSs we might boot?
So are you saying like what happens if we boot Windows on the same OS? Windows on the same firmware?
Yeah, or a different version of Linux, or with a different set of drivers, or.
So I think it's the same problem as like properties today. Any other property, if it is standardized, it has a semantic meaning. So whatever is the process to introduce a new property, it would be the same. So for example, today, for example, we are using Microsoft spec to specify external facing ports. That is what Linux uses.
Right. I mean, externality is, I mean, that's an unambiguous thing that, you know, there's no question of whether it is or isn't, but trustedness seems like it's a function of maybe of both the device and the driver, and I'm not sure that you could reliably describe that in firmware that doesn't know what the driver is going to be.
So essentially our options are limited to, like if we don't want to put that knowledge in kernel, the options are limited to either user space tells us or we get it from platform somehow.
Yeah. Yeah, I don't want to rat hole on this, so let me give some time to Robin.
Yeah, well, I think that ties into what I wanted to bring up, which is also based on what Doug was saying on the list earlier, that we might actually need more than one degree of trust here, because so we have, you know, the obvious case is that we want to deal with like the external Thunderbolt PCI devices that could be anything pretending to be anything else. But then there's also things like on-chip accelerators where you trust that the hardware is okay, but you don't necessarily trust the vendor's firmware blob not to misbehave. So yeah, you're happy to bind a driver to that device, but you want to make sure it still has strict Iommu protection and doesn't get the chance to just run all over memory accidentally.
Yes, this flag will then help differentiate between such devices. If like a driver can bind to multiple devices, one of which you want to keep trusted and one of which you don't, this flag can help you there.
And there was also the thing where this might depend on the user perspective more than the platform. So, you know, a first-party device is going to say, yeah, we trust this firmware because we wrote it. But then you put the same SoC in a third-party device that's marketed more security-focused, like some of the phones coming out, and they're going to say, hey, this is a binary blob. We don't want to trust it so much. So yeah, that definitely points towards wanting some kind of user level override that's not necessarily as ugly as having to put massive strings on the command line.
I agree. So we need some way to put it from user space. The problems are that essentially the SysFS comes up only after the user space is up, and if there are devices in the boot path that you want to that need attaching to a driver, then there is little we can do. I am actually running short, so I wanted to rush forward to the real meaty part where actually I needed inputs. So so one thing is that as I mentioned, so currently there is no good solution for devices in the boot path. In the boot path, since there is no user space to tell or alter or override, so the only options are either get whatever information you need from firmware or you need it from command line. So that is one problem that I have not found a good solution to. But what I wanted to discuss here was the other thing that we discussed a lot on the mailing lists about how can we make this work for at least other devices, that is the devices which are hot plugged after boot, or where we wanted to borrow some infrastructure from USB and bring it into device core. So just to make some quick points on this slide, there is no good solution for devices in boot paths today. And the untrusted or the location, whatever you want to call it. So today they need to be consumed. They need to be consumed early on by the Iommu or PCI drivers, at least before their drivers begin to attach. So any solution that we propose that would need to allow the devices to enumerate but stop before attaching to a device, at least before attaching to a device. After that, it should allow the user space to change whatever parameters it wants to change. If it wants to implement a policy, for example, if it wants to, let's say, allow it to attach to only certain drivers, like if you want to have it, if you want the user space to implement a policy so that only certain drivers are allowed, or if you want to implement any other policy, for example, if it wants to pop up a blocker to the user and let the user select, yes, I want to enable this device, whatever the policy is being. So we have to let the user space do that, and then a way for the user space to say, go ahead and enable this device. When it says that, just before that, the PCI or Iommu will need to now consume the fields that the user has changed. So with that, we have given the opportunity to the user to change. So in this context, the user might be changing the untrusted or the location. So essentially, the third bullet is what I wanted to highlight here. So any solution that we do, that it would have to pause the enumeration process and binding to the drivers. It would have to give the user space a chance to change whatever attributes it wanted to change and implement any policy. And then a way for the users to say, go ahead and attach the drivers, at which point PCI Mmu will now consume the fields that it needs to. Yeah. So the options that I considered and that were suggested and came up during the discussions was, USB already has a authorized and default authorized UAPI that Greg is not here. Okay. USB already has an authorized and default authorized UAPI that fits the bill to a large degree semantically. Essentially, USB authorized API, what it does is it allows us to authorize devices and deauthorize devices Deauthorization means the device is disabled and not bound to any, not allowed to bound to any drivers. And only when you authorize it, then that's when it allows you to bind to devices. But there are certain problems with using this, or at least some challenges that I wanted to highlight and discuss. So one thing is that USB authorized UAPI is very well used, and there are tools in user space. There's USB guard. There are some others, and there is another authorized attribute from Thunderbolt. So they have a conflict there of the UAPI. So how do we deal with this? The other thing is, in today's UAPI, it's an end device thing. So there is no devices hanging downstream a device. So but if we were to move it to driver device core, if we deauthorize a device, we would need to deauthorize all its children. And on the authorization path, if we want to authorize a device, so in the current UAPI model, the user needs to actually enable all the bind all the drivers manually by kicking the driver underscore probe property. So it may be a little tricky for the user to iterate over all the children and bind all the drivers manually. It could pose some race conditions. The third very important is that currently UAPI is widely used, and I'm worried that we might need to make some changes to the UAPI to match the new needs, because currently it is only location based. So currently it allows there is a policy that allows us to so in USB you can set policy that only by default only either all devices are authorized, or none of the devices are authorized, or internal devices are authorized. So if we want to change it not to location but to an untrusted device, I'm worried that we might need to make some changes to the UAPI, and we might not want to break any existing UAPI users. Last is, it may need much wider discussion and buy-in from Thunderbolt driver folks or from user space tools and effort. So if we have to go this way, I would need some help in finalizing a UAPI that is acceptable to all. That was the first option, and I would have Greg's comment on this. He's not here, but the other option that was suggested was drivers auto probe. Drivers auto probe is a mechanism that is used that should be usable to use, that should be usable to disable auto probe of devices, that is auto binding of devices to drivers. But it doesn't work for PCI today because PCI uses device attach, and that does not honor auto probe, because device attach, I think driver core uses as an indication to say that bus is explicitly wanting to attach a driver to a device. So these were the main current challenges that I wanted some inputs on. Beyond, do you have any inputs? Or I have 3 minutes remaining. Beyond, do you have any inputs or comments here?
Yeah, I was just looking back at your first slides about what we want to do based on this external or untrusted flag, and some of it is has to do with disabling ATS and so on, and some of it seems to be preventing binding of drivers to a device. So there's, I think, a couple things we're trying to accomplish here. One is, and I don't think you mentioned it here, but if in the mailing list, I think you did, about preventing drivers that you're not confident have been hardened from binding to a device, and that's useful. But there's another objective that is independent of driver binding, and that is defending against malicious devices that can do DMA. Those devices can do DMA regardless of whether there's a driver bound, and so I think we should consider that as well as the driver binding question.
Do you mean the driver allowance? I thought that was shot down long ago.
Say again, I didn't catch that.
Did you mean a driver allow list in kernel, or are you saying the?
No, I'm saying even if there's no driver, if you plug in an external Thunderbolt device, with no driver at all,
Mhm.
A malicious device can do DMA. So we're exposed there, and I think that's a case that we should consider when we're trying to figure out what to do here.
So I think that case is taken care by the Iommu restrictions that we have in place and the PCI ACS restrictions. We disable ATS today.
Oh, that's already covered?
Yeah, so I think that is already covered.
Okay.
Because we are, at least on Intel IMMUs, I can say that we are disabling ATS, setting up bounce buffers, and we are treating all IMMUs as strict for external devices or untrusted devices.
Okay. Yeah, I remember we talked about that, but I didn't remember the outcome, I guess.
There is one patch that is pending which says like disable transaction, disable address translation, disable address translated addresses. That is pending.
Right. Right.
I think I'm out of time, so yeah.
I have to stop it, unfortunately, Rajat. I mean, but I think we should try to come up with a follow-up discussion either in hack rooms or BOF. I mean, one of these days. I don't know. We can organize it if you wish. So, I mean, because it's an interesting discussion, and I think, well, it was a starting point.
Sure.
Yeah. Thanks
so,
a lot.
I'll be sending some mails on the upstream mailing list about this. Thank you so much.
Thank you. Sergey, you should be able to present now, so I think the floor is yours. Feel free to go anytime.
Yeah, thank you. Hello, everyone. Can you hear me? Please let me know if you can hear me.
Yeah, we can. A bit of echo, yes, but it works.
Oh, thank you. So, thank you for inviting me. And here I want to discuss two large things. First one is movable bars, and second one movable bus numbers. And let's start with bars, as they seems to be as problematic. So I want to present very quickly this review of all this feature, what's going on those more than 20 patches of the series. So for a review, and probably we can find any flaws in this approach. So why does hot plug hurts so much? One of the reasons is because of the need to map this tree structure of the PCI topology into this linear address space for PCI. So when a new device is attached to the topology, its bars cannot be put just somewhere of an address space like here. It must be attached to the window of a downstream port of its direct switch where this device is attached. And this window may have not enough space, or if it is fragmented or or any reasons. Constructing this mapping, assigning bars and bridge windows from the scratch during system boot is relatively simple. Because all we need to do is two steps. First step is calculate size of every window, and it is roughly size of a window roughly is total size of every bar, and so on. And the second step is having all windows sized. Just assign them to some address. Usually, this process of assignment is already done during system start by a bootloader or BIOS or UAPI, and but at least for some platforms, kernel is also able to do this by its own means. Usually to overcome this problem of not enough space in the window is solved by requesting a larger window than it should be. So it has some gaps, free gaps, where new bars can be fit. Okay. But with these reserved spaces, it mostly works for endpoint devices. But even when adds in a GPU, which has a huge bars sometimes, it may not fit even with this. And when attaching with some chassis full of devices, it doesn't make things easier. So, if the kernel is already have means to reassign all the bars, why not just, like it does during the system boot, why not just reuse this algorithm? But this time, when modifying the existing assignment, not all bars can be moved. And some of them, most of them actually, are most likely already bound by some driver, and driver works with these devices, and so bars cannot be stopped. They must remain on their places. And the I/O with this device should go on, must go on. So if device is already bound to the driver, if the driver doesn't explicitly support this feature of movable bars, I will come to this a bit later, these bars are considered fixed, not movable. And the rest can release and reshuffle to make space, to probably arrange some space for new devices. Okay, so let's go on. So, effects of these changes: if previously free gaps were already pre-arranged for every switch port, when a new device arrives, it's almost no need to touch any PCI registers, any hardware. So almost the only things to do is just to set up its new device, and that's all. But when the bars are movable and they can be reshuffled on the running system, we have this process may affect completely all the tree, because bridge windows will be moved, bars may be moved, shuffled. So it's every local events of hot plug starts a sequence of complete bus PCI scan. So in the beginning of this process, all the drivers which support movable bars must be paused if they're pausable, and after that they must be restarted. Again, so how to, when calculating, so coming to first step of calculating sizes of every window, there is one pitfall when doing this, like it's depicted here. So size of a window, is sometimes not equal to total size of every bar. So in this situation, to solve this, I have to introduce a new field in the struct PCI bus, is fixed range. This fixed range is represents the spread of all bars below this window. Next, when calculating when this new bar may reside, new window may not move too far away from the fixed bars. So, like here are first same bars. There's two variants of how it can be, like polar ways of how it can be assigned. So here we need this margin, or this minimum address when window can be assigned. Luckily, the kernel already has an interface. So when assigning, having this argument of minimum leftmost address when the window can start. So during the calculation, we can just use this margin. What I didn't mention, at the start of the PCI scan, we need to free all the windows because they will be recalculated, their positions and their size. They will be recreated. And the movable bars are also released. By releasing, I mean not yet touching the PCI registers configuration space, but only touching structures in memory representing them. So this struct PCI bus, instruct resource, and this break the links in parent and child between them. But the hardware is not modified anymore yet, because there still have to be I/O ongoing to the devices which remain their bars fixed, because drivers are not prepared yet. And in step 2, when the window size are calculated, they cannot be assigned to some addresses in arbitrary order, because sometimes it gets to unlucky results and failure of this whole procedure. So when assigning addresses, the windows must be sorted before. Again, luckily, this procedure of sorting before assignment already exists in kernel internal API. So the only way I need to modify is to start considering this fixed range, this range of fixed bars below the bars, and that one which has leftmost, like earliest address of fixed bars, will be assigned first. So on this example, this leftmost window will be assigned first, then windows of switches below it, then within this window, after the fixed bar, it will be all movable bars assigned. After that, we can next step is assign this second set of starting from a downstream port, downstream root port, and so on. And the last part, we have all movable bars, and they can be assigned in any suitable position in this PCI address space. And only now, when the preparation is already finished, only now we can write all these positions, addresses of bars and windows to the hardware. Not earlier. Up to this moment, it was possible to make it with relatively minor modification of the code in the kernel. But the pitfall is still, if some bars movable, it is not always guaranteed result of bar assignment. If other space is still fragmented by fixed bars, or it's not enough other space. So if the procedure fails, we need to fall back and use previous layout of bars. It may not necessarily be the exact layout, but still some working. To make it possible, I introduced for each PCI device a new bit mask. Bit mask of all bars that worked before the scan. And so we can retry our assignment without those bars, without new devices. So if this kernel algorithm succeeded before, it will succeed again with the same set. Also, it is useful because some BIOSes consider that we don't need all the bars, and it assigns only parts of them, and leaving no gaps for the remaining ones. So during the system boot, we cannot assign those. In this case, it is also useful to start the system full PCI scan during the system boot, so we can assign all of the bars. So that makes a need sometimes to run rescan trials several times. First one is to try every possible bars, all requested ones. And if it is not possible, then retry without those bars that wasn't assigned before. And even this still fails, we need to try to disable bars for new hot added devices and try until all of them are disabled, and we just return to a previous layout. So this is an example of implementation of what needs to be done in drivers to implement this feature. The only 3 hooks need to be added to PCI driver structure. And the essential one is bar fixed, which returns bool. So which turns is this bar fixed already. One of the trivial example is the driver of the PCI switch, PCI Express switch, which is trivial because it's even if switch have bars, but the driver doesn't use them, they can be released and reassigned later. And here is an example for an NVMe driver. So first, we need to, before the scan, we need to pause it and unmap the bars, and when the scan is done, we need to call asynchronous reset. Oh, sorry, I don't have too many times, so before. Sorry?
Sergey, I think it's very interesting. I will move to the bus reallocation as well, because in 10 minutes I think you can at least broach the idea, and then we can discuss.
Okay, so that is not so interesting. So let's go to the second part, which seems to be much more problematic. So movable bus numbers are very similar because as well as bars, it has start and ending limits. And to make it possible to add some bridge, just like this one, we need to use some range of free buses to put it. But if this bridge is some chassis of devices, or worse, it is a nested switches with devices, this reservation of bars may be not enough still. And it sees we have limited sets. So the maximum bus number is 255, so it's not so much. And it doesn't matter how we reserve them, still always a chance to break this. As a proof of concept, we've tried the following approach. So when trying to attach the bridge, instead of reserving bus numbers, each time in the process of adding this bridge, when a new bus number is requested, we move like this tail of the tree. So habits. Move it lower, so one new bus number gets freed. So in total, if the last number of the new bridge was 1Z, like this. So this tail of the tree is one bus number that was 4, it gets 1E, and so on. From a device driver's point of view, it may be a bit safer because they need to be actually paused before this. So because the device addresses are not used directly usually via this PCI device handler. Still maybe need to block some accesses. But the real issue is these guys. These guys in SysFS and Linux and ProcFS. Because if device address has changed, all these guys must be changed as well. And this, as I understand it, is breakage of API, and this, probably people will not like it too much. Still, if we assume that this is possible, that what we wanted to experiment with this a bit. As expected, there is not much functions in kernel API to rename devices and do this job, except to device rename with this market with donut call this function. And creating these files performed during this attaching new device to the bus, like here. And also the rest of the function was just called from there. But so the approach was just to test things if they will work, was to detach the device from its bus but leaving all drivers and all user space using this driver remain. So if it was network interface, if it was network card, its network interface remains in the space. If it was a block driver, it remains in the def NVMe something. So I have to go this brutal way just to try to, for as an experiment, to create a new kernel API, like this bus disconnect device, which is very same to remove device, but that doesn't have this release driver, which you actually detach the driver from device, because it breaks things on. And it makes things functions as local to this driver's base tree. So it makes it public to make this possible. So experiment shows that it was kind of succeeded, because if when calling this Fio to these both devices for an experiment, and in this time running this PCI scan, the devices were still working. So NVMe, as they paused, they have the throughput paused for drop into zero for a while. Okay, got it. But then it restores. So without actually errors of communicating and so on. And if running an SSH connection to the system and running PCI scan on the same system, so the SSH connection didn't actually break. So it just continue working this. So it was quite an adventure, but it was totally worth it. So that's what I wanted to bring to a review. I hope lots of you have something to add to this.
I have a question back on your fixed bar interface.
Yes.
How do we handle peer-to-peer with that? How does a driver know whether their bars might be a peer-to-peer target, and how if the hierarchy is not, if the peer-to-peer pair is not in the same hierarchy, how does that work?
Well, for P2P, it's still some driver attached, I guess, which handles this. And this, so by default, all the drivers must opt into this feature. And so if this P2P feature is from bound to some driver, it will not let this bars to be moved.
But how does like I'm thinking of the VFIO case where I have a generic driver where I can prevent the user access to the bars, but I have no idea if the bar is also being used by another device. So in a peer-to-peer scenario. So does that mean that I could never opt into this scenario? And for a regular device driver, I don't know how much they're aware of peer-to-peer as well.
That's a question that I don't have an answer now on it. So here I'm got stuck a little with this question.
Sergey, I think I was also mentioning about the new flattening portal bridge. Yes, that requires new hardware, and I think it's now we at least in Intel we have some new client platforms, especially for Thunderbolt. This becomes a lot more required, right? And I think that might be one that we can probably take a look at. But in this current cases that you point out, when you do the rebalance dynamically, you really need to actually kind of bring down drivers and bring them back up and things like that, right? Did I understand you correctly?
Actually, Sorry, I got stuck a little bit. Would you please repeat this question once more? Just.
I think you're talking about what's on the screen right now, aren't you, Ishak? Where the driver has to, the rescan prepare callback is called before the bars are moved, and then the rescan done is called afterwards.
That is correct, yeah.
So were you pointing to a problem there, or just?
Well, just kind of asking that, that when we do the rebalance that drivers do, it's a noticeable change in the system that things kind of need to be quest, and then
right.
Things needs to come back up. It's not, so there is system level impact. This is what I was trying to kind of,
yeah, definitely.
Yeah.
Unfortunately, guys, I need to ask you to wrap it up. I mean, I don't know how you can. I suppose we should follow on with this discussion. I mean, in the hack rooms as well, because I think it's an interesting issue to be solved. So, I mean, feel free to reach out. I mean, through the usual channels so that we can bring it to completion. At least I think it's useful to define the problem. I mean, then how to tackle it, and we can see the way forward.
Okay.
Just one quick question, Suchi. So when you do this rebalancing on a reboot, actually, do you kind of preserve these settings so that you don't need to do this again, actually, or how do we remember that what we went through now is good for the next session when you come back after a reboot?
Actually, it's not preserved. It's can do it from scratch every time. You just need to have listed bars that we need to assign before. So the bars that was working before, or was comparing to those set of bars that we desire to assign right now in this the next attempt.
Okay.
Well, again, sorry for stopping the presentation, but I have to, I think we reconvene in 10 minutes. I mean, quarter past the hour with Sean presenting AR.
Okay, bye.
Hey, Jonathan, looking forward to you joining me in this discussion.
I'll get some quick answers out of Bjorn.
Yep.
Good in Dell.
This is a good opportunity. So.
So Sean, now you should be all set. You're ready to go. Thank you very much.
Yeah, good. Hey, my name is Sean Kelly, and you know, in the course of looking into compute express link support, I was plumbing, you know, what are some of the gaps, you know, what are some of the things that we're missing in the kernel today that will be necessary actually to support these sort of CXL class devices. And one of the things that came up was the root complex event collectors. It's kind of interesting to see that Linux actually doesn't have a lot of support for it. In fact, if you kind of look through the history, there'd actually been some patches to remove some capabilities because there were no devices that were really being used for it, even though it's optionally a part of the spec. Even when looking for hardware that actually kind of supports, you know, RCECs, it's kind of hard to find and they're scarce. There was a Denverton system, but even that didn't have, you know, support for some of the extended capabilities. So root complex event collectors. So basically, they provide support for the terminating air conditions and PME messages from a root complex integrated endpoint, and that's just a fancy way of saying something like an accelerator card, something like a graphics card, something like, in the case of CXL, like a Type 3 memory device, right? And it resides on the root complex. And the interesting thing about that is, too, it has these RCIPs associated with it. So an RCEC will have sort of an explicit declaration of all of its supported integrated endpoints, and those kind of hang off a bitmap. And initially, with the PCIe spec, that was just it. They were always on the same bus as the root complex event collector. But then as we moved into PCIe 5.0 spec, you could see the extended capabilities, which brought on the ability to actually have these endpoints existing on other buses. So you could have a last and a next bus, and you could have sort of a range of buses on which these endpoints, integrated endpoints, could actually reside. And then the next step around that is, you know, how do we bring sort of support when you think about, you know, these root complex event collectors and the messages and the errors you want to manage? How do we get those, you know, detected? How do we manage those? And remarkably enough, as you probably already know, when you look at things like the PCI port driver, root port driver, and you look at things like AIR or PME service drivers, you see that all those are all port centric, which makes sense. You got your upstream port, downstream port. That's all that existed, and that's all that's really there. Fortunately, the way that it was handled after talking to, various folks, it looked like that, hey, we could probably extend the port driver to include the class of root complex event collectors. We could extend the service drivers, right, so that we bind those objects to the drivers for the root port to be able to provide those services for the root complex event collectors when we actually get those errors. And putting these pieces together, the focus of today's discussion is really to talk a little bit about the native cases versus the non-native case. Now, from an ARM perspective, you might think about what's, native versus non-native. Oh, you mean maybe firmware first versus kernel first, right? So it all depends on your how you're actually trying to describe it, but ultimately it means who's going to actually get the error, who's actually going to get the information first, right? And so in the course of reviewing, submitting patches and getting feedback and discussing them on the list, one of the topics that came up is actually getting Jonathan Cameron's work with root complex event collectors. Like I mentioned, as I started to peruse and look to see where RCECs have been mentioned, where work has been done, the timing was perfect because Jonathan himself had been looking into that case as well with regards to RCECs, albeit from a firmware first or a non-native use case. So today's talk is going to be kind of centering around the intersection of doing recovery, PCIe do recovery, as well as looking at situations where if in a firmware first condition we don't actually have an RCEC, there's no actual registers or bits to clear, what do we do? So that's what we're going to talk about. So on the native case, so the native case is that you could imagine some device, it could be a CXL type 2 device, an accelerator with some memory, and it's hanging off the bus, and you've got some function with an error that's asserted. So these errors are logged in the local error extended capability per function, and what happens is that those will eventually get messaged to the RCEC. The RCE logs the errors and could generate an MSI if enabled. The trick here is that when an RCEC device sort of signals the errors to the CPU core, the core needs to basically figure out, hey, which endpoint is this associated with, right? And that's where PCIe extended capabilities come into play, where you can walk the bitmap or walk the bus numbers to actually identify and find, the actual, there's two things. One is you want to be able to identify the source of the error, but in addition to identifying the source of the error, you want to be able to know the RCEC that's linked, so to speak, to the endpoint, so that for purposes of clearing the root port status error bits, right? And so again, this is sort of like the flow, so to speak, in the native case today. And this is primarily hardware based, so RCECs are hardware features, so there is a finite number of them, and they can have up to, according to the spec, up to 32 devices. The interesting thing about RCECs that people should be aware of is that an RCEC can also have its own error. So that when you actually look in the PCIe spec, and I listed the, if you look at my backup, you can see the patch series, and I really encourage you to take a look. You can see that RCECs themselves can also report errors as well. So it's not just the endpoint itself, but also the RCEC, much like a port, or bridge, can actually report an error. And then the non-native case is one in which you have an APEI. So it's essentially error via this sort of ACPI platform error interface. And in these cases, an RCEC may not even exist, and the platform could have a hardware entity performing the role. It's really opaque to the OS at this point. And so it doesn't have really any visible association to the actual device itself. And so the trick then is to understand, how do we actually manage sort of like the PCI do recovery in those sort of cases, these non-native cases, and how does that coexist with the existing native support? So the purposes of really the discussion and why I wanted to bring this topic today is sort of on the error recovery. So when we're attempting error recovery for an RC IEP associated with a native device, we really have to have a way to update the error status and severity. But depending on the native versus the non-native case, it may be that, you know, the expected error registers don't even exist. And so in the discussion we've had online, you know, we've talked a little bit about bridges and the devices. So bridge, which is actually a better word than port, as I was sort of plumbing out the port driver support, the air support, and the PME support, Bjorn actually, you know, pointed out things like, hey, let's think in these terms of bridges. And so as we look at the bridges could point to the device, like the root port, you know, the downstream port, and so on. It can also be associated with the RCIEP's own RCEC, which is the pointer back, so to speak, to the RCEC. And it may not even exist. So part of today's discussion is really kind of centered around, you know, what additional considerations should be considered or addressed in handling the call to PCI do recovery, including this subsequent reset if needed. There are some other ancillary topics which have to do with, you know, how do we describe this? You know, when we look at these devices or bridges, we looked at the bridge and say, are there any subordinate, you know, any sort of subordinates buses, you know, below it? And that's kind of where this all comes about when we talk about walking the device, when we look at, and this is where Cameron came in as well, looking into, hey, we have a subordinate device that doesn't exist in this case, but we need to handle it. And then I came in as well, where picking up some of the work from Cameron and building on that for the native case. And so I'm opening the discussion to Bjorn and Cameron to kind of hopefully kind of sort out and discuss some of these trade-offs.
Yeah, thanks a lot for working on this stuff, to both of you. This whole area has been a perennial issue, and it's not been well supported, and yeah. I don't have good confidence that it works well, so I'm glad that there's more work going on here. One thing that's confusing to me, just because I don't work in it every day, is what the argument to PCIe do recovery is. I think in most cases it's the endpoint, but then inside there we back up to the bridge that leads to it, and then we, if I remember correctly, we go through and reset all the subordinate devices. And I don't even,
yeah, we reset the link.
Why do that? I mean, it doesn't seem to me like all of them need a reset. It seems like we ought to be able to selectively reset the one that we care about, but there's probably a reason for that. I just don't remember it, and there's no comment. So
there's one classic that causes trouble there is, although the spec allows for you to report multiple sources for AER messages, well, Linux certainly doesn't support it, and chances are no one's ever built any hardware that actually does it. So one problem you have is once you've got an AER message has come in theory you've got in the root port a description of where it came from, but you've no idea what else just happened. So you have to go out and walk the bus and find out who's got any problems. Now, in this particular case, it's kind of easier because there isn't really a bus. I would say, almost when discussing this, I'd just look at a normal RCI boot complex integrated endpoint, because CXL brings a whole load of pain on top. There's various bits of topology that are invisible to the OS. Yeah. But for a normal case, it's just usually part of the SOC. So there's no actual bus there, which gets into interesting questions of what the heck does link reset mean?
Right. What does it mean for this device exactly?
Yeah. But even in the normal case, there's very little documentation of what the reset path should look like anyway when you get an AER error. I think it looks like it's kind of evolved to something that works rather than.
Right. Yeah, exactly.
So yeah, there's a couple of sticky questions of what you should do. I mean, couple of things to note as well is in the API case, you might actually have a root complex event collector, but you shouldn't touch it. In the same sense that for a normal endpoint, you shouldn't be touching anything to do with the root, whoever received the AER message, because that's up to firmware to deal with. But that's just a subtlety. So it looks nice in LSPCI, but otherwise we should not do anything at all with that.
Right, right. So my hope is, well, I'll tell you what I'm thinking long term, and you can tell me what's wrong with it. Is we have this firmware first model or APEI reporting, which I'm not a BIOS guy, but my understanding is basically that means the firmware read the error registers, packaged them up, cleared them or whatever, and then sends that packet off to the OS. So in my mind, the ideal thing would be is that in the native case, the OS reads the registers, packages them up, clears them, and sends that packet into the same path that the API path does. And today they're not quite the same, and we have issues related to that. For example, we in some cases get a storm where we fail to clear the status register when we don't find the endpoint that reported it or something like that. I think if we could consolidate the front end of that path, we could potentially solve that and simplify the whole thing.
Yeah.
But that's kind of a long-term thing. I don't expect that to happen, in this patch.
Yeah.
Yeah. I can see where it come from. The one thing you're kind of assuming with firmware first is that you don't get the multiple error case for this case anyway, because you've no way of knowing about it, because you've got none of those mappings to know that some bit of hardware that you received. I mean, if we think of the API case as actually just being RC EC exactly the same as the native case, just that you're not meant to read it and the firmware does it, you've got the same problems around detection of multiple errors, and there's an assumption in there that you can handle that. Frankly, if not, you're dead. At least you detect you've got multiple errors and you die hard if you failed to handle them because there's nothing else you can do. So
you mean multiple errors from the same device or multiple errors from different devices?
Different devices. So you've got two different integrated endpoints. They've both faulted at the same time, but you've only got one thing, that's one set of registers reporting what happened.
And that's actually possible then, because you have the root they're all pointing to the same root complex event collector at that point.
And
yes,
and you would actually
you expect you're okay because you walk them all to check.
You're gonna walk them all and find out.
There's some horrible races around that, but hopefully you walk them all and check them all.
Yeah.
As long as it's right one to clear the event, you're probably good.
Yes, assuming you've written your firmware right, it should all work. But I wouldn't guarantee it's true. But you do have to do a little bit more walking. Yeah, I mean, it's not a very simple one packet flow for the case where we're doing the native handling. There isn't. It isn't necessarily possible to wrap it all up. Although I suppose you could walk the bus, work out all of the errors that have occurred, and send them one after another. I don't know. But as Bjorn said, I think that's a good long-term one.
And I think with EDPC, we also have the quasi-handling case, right, where the notification is sent from the firmware, but the real recovery is done by the OS, actually.
Yes.
Yeah.
For EDR, you mean?
EDR.
Correct.
Yeah.
I think we also have a slight problem at the moment is I don't know how much hardware Sean's got access to, but
yeah,
I mean, I have some old hardware, but a lot of this discussion is about stuff that's coming.
Right. So I have access to real hardware that I'm testing this on. You know, and like I said, it's like a finite number of RCECs, and I just test with various integrated endpoints. But I think one thing that I would like to do is make the reset aspects a little more clear and plain, like we talked about reset link, and we talked about, I mean, I like the idea of reset subordinate or something like that, just to make it a little more clear about, you know, what you're actually doing and what's going on. I like the terminology in terms of bridge, and also bringing in the perception that, hey, there is no bridge in this case, so it's really just the device that we have to handle. But I also like Bjorn's long-term suggestions on how can, you know, we make this clear, because it's kind of nebulous at this point. It's kind of like we wave our hands and we reset the whole link and connection. Maybe we really don't have to. It's just that we've done this before, you know. So
yeah, one quick note before Srinivas gets in, but that could be that's related to when we consolidated kind of the AER and the DPC case, where DPC does the reset link for you.
Yeah. Yes.
Do it similarly.
Okay. Well, on the backups, again, I have links to the discussion for what we talked about today, and encourage others to weigh in and participate, and then also just the current patch series as well. Thank you very much, everyone.
Thanks, Sean. Thanks, Bill.
Thank you very much, everyone. Thank you very much. Ashok, whenever you're ready, you feel free to go. Thank you very much.
Sounds good. Ready to go, Lorenzo?
Yes, yes, you are.
Right. Okay, so you know, this one is probably a less controversial topic compared to what we had the session start with. So basically, we have one of the things that we are trying to do is trying to decouple certain things that the Iommu driver was doing implicitly during you know, device attach time, and move them a little bit later into the device driver, you know, kind of framework. And there are certain good reasons to do it. Just want to see, you know, what Jörg and others actually think about it, and kind of, you know, take it from there. So this is mostly for other people not to harass me actually while presenting, but nothing other than that. Just gonna flip through this one. So okay, so so today, you know, when we do the device attach with Iommu, certain PCI capabilities get enabled automatically. Like, you know, for instance, PASID, and we need to also coordinate that PASID is enabled before ATS. But you know, if there is an issue with the device and the device driver performs FLR, the restore state and things like that are driven by the device driver itself, in terms of, you know, putting things back in shape, right? And one of the things that we're looking at is, you know, for instance, if for example, maybe, you know, on a device ATS is maybe broken, right? And the device driver actually knows it already. And when the Iommu driver is automatically doing it, that means we would need to put some kind of a quirk or some mechanism to say, you know, don't turn on ATS on this device. Now that becomes a lot more simpler and managed by the device driver itself if, you know, if he's already knowledgeable that this particular device might be broken, and applying any filters before they enable the Iommu functionality for that, right? The other thing is that some of these features, you know, like PASID, PRI, and ATS, they all require Iommu functionality, and especially when we add a scalable IOV. We currently have a vendor-specific extension, DVSec capability that says, yes, I support SRIOV, scalable IOV, but there isn't any good indication to say whether the Iommu has enabled those features or not. So for instance, we could actually have disabled ATS in the command line, right? And the Iommu driver would actually make sure that is enforced, but the device driver isn't knowledgeable that do I even have an Iommu upfront, right? Or do I have an Iommu that supports these capabilities exposed, or has the command line parameter something been turned off, and now in my current system I don't have these features available, right? Some of these discovery mechanisms are sort of convoluted today, and we don't necessarily do a good job of the device driver putting them in the path of controlling the features that they want to enable or disable for certain functionalities. Some proposed solutions is that that we can probably extend. There are some similar things that we added for the aux domain capability, for instance. But aux domain is more of a big chunk bolt that just checks whether facet PRI or these things are enabled, but they are not independently discoverable or controllable up above. So the device driver doesn't even have a chance. And like I said, there may be a device that says, hey, I really need ATS to be even functional, even though it's an optional PCIe feature, but the driver has no say today the way it is structured to actually enforce those checks. So some of the suggestion is kind of exposing, the API part just is something I threw up there just for discussion, but the names and things like that could be different. So the driver could actually say, is the Iommu support these capabilities, right? And it can check whether the Iommu is capable of it, and also whether the device is capable of it, and all those neat things. And they can, pass in features that they are actually interested in. And then they would have a separate independent step where you enable these capabilities, and that is where we actually would go and turn it on the context entry for those devices. So Iommu can actually supplement those functionalities, and also enabling it on the device side, right? So that's the current thought actually. It's just basically the functionality is already there, but we just do it implicit in the Iommu code, right? And the request is to actually move things to more of a device-initiated discovery and enabling path. Okay, that's pretty much it. And I would like to see if Jorg is online and kind of get his feedback actually on those things.
So you want the endpoint device driver to enable this PSID PRI ATS features, right? Isn't it enabled to just have functions for all of them to check, to allow the endpoint device driver to check whether they are enabled, or do you really need to enable them from the device driver?
The request to do this from the device driver is two independent reasons, right? So for instance, the device may have its ATS functionality present, but it's buggy, for instance. So at a later time, the device driver says, I really want to opt out of this thing. And the only way we can do that is put a new Quark infrastructure somewhere there. So the Iommu driver can check this and say, oh, this driver is in the disallowed list, and then turn off ATS or not enable ATS for those. It's kind of a convoluted way to achieve the same thing versus letting the control in the device driver. They know they can actually just implement that that correctness from there. The other thing is also that ATS may be present, but the device driver wants to make sure that it is actually enabled in the Iommu and also on the device, right? So yes, they can go independently check the PCI device and say, is it enabled or not? Did the Iommu driver do this thing or not? Versus letting the control just always flow through the Iommu path for the enabling. So that way, if the enable is succeeding, then I know that my device is ready and my Iommu is also plumbed in for these features, and then go out. And PRI for the same thing, right? It could be PRI is there in the device, but maybe my system is buggy and I device driver says like, I just want to do only passive and ATS, but I really don't care about the SVM or the paging aspects of it. It gives driver much more finer control on what is and what is not enabled, actually. That's all. And there are some class of devices, I think, that might be coming from us that might need that level of control, actually.
Okay, so for PRI, the IOMU driver needs to have a say because it needs to allocate a portion of the page queue, actually, right?
It's not on a per device basis. The IMMU enabling page request is a different. It's a global setting per IMMU. It's just that whether PRI is plumbed in the context entry for this particular device in question, right? So when PRI comes, actually we can find out whether this device has enabled it or not. If the device enable is not there, IMMU would automatically reject that and treat it as a fault condition, actually, right? A recoverable fault. That's what it is. So we don't necessarily even enable it on the device if we don't need it to.
Can we just wrap this into a SVA enabling functionality? And if the device driver knows of a device that is misfunctioning on any of those capabilities, then it just doesn't call this SVA enabling function.
Right. For PRI, it sort of makes sense. But for ATS or passive, so a device may be also, PRI capable, but I'm saying like, I want to use it just as a scalable IOV function where I'm going to do, sub-device pass-through, for instance, where passive and ATS are required, but PRI is not required, right? So bind will automatically fail, bind MM or whatever it is that we call it today will fail, but I still have final control on the other two aspects of it. So rather than just doing one, we'll just let the device driver control all aspects of its functionality and coordinate with the IMMU driver just to enable it at boot time. Like once it comes up and during the probe time, he'll say like, I want you to enable these things, and then it's all done actually. Today we just do this during discovery time, and it's too late for the device driver to even participate in that actually, right?
Okay, so yeah, I'm not strongly opposed to it, but I'm still 100% convinced that it's necessary. So
okay.
So do you want the CAP supported the IOMU enable CAPS function to allow overriding settings like ATS disable? Or will it just fail in this case?
We don't want that to override ATS disable. So if the command line parameter says ATS disable at the command line, this function would also fail enabling it. Actually, it'll still support what the high level override is. We don't want to go underneath the cover and change things.
And also, it would fail on untrusted devices, right?
Right. Whatever the high level policy is implemented, it would still honor those capabilities. Yeah, we are. This is only just purely a feature enabling thing. And if the policy for trusted or untrusted allows ATS, then we are good to go. If that is disallowed or the command line ATS is disabled, these capability enabling will fail automatically. And that's the idea actually. So we just want to enforce what the system level policy guidance is from user space or command line. But these are just pure plumbing between the IMMU and the device itself, that the device driver gets a chance to dictate, both for error reasons or errata reasons, managing it, or for just limiting functionality between some aspects of it. That's the whole idea. I think maybe once we have some POC code or something like that, I think Alan will actually send things out. And we can kind of discuss this in the community. I think this is not too controversial in the sense, but I just want to throw out the need for these and why do we need them actually to get some direction.
I'm not buying into the device quirk thing because we already have the PCI quirks and we already have a disabled ATS quirk, which can just be extended for devices which have buggy ATS implementations. So.
Okay.
So actually, for ATS, the PCI ATS enabled thing would probably be enough for the Ford driver, right? Just checking if it's enabled or not, and if not, do whatever it needs to do. Or if it's enabled, enable the feature that require ATS.
Yeah.
Things are different for PRI and Face ID. If it's really needed, I would prefer specific functions, not a generic enable caps function, just specific functions for these two capabilities.
Sounds good. I think that'll be a good start actually. The only reason I moved in ATS also is like, rather than adding more to the quirk actually with the BDF and all that other stuff, actually we might be able to let the device driver manage its own deficiency in functionality versus having to bolt another one, which I know that the quirk already exists, but this kind of let it move that capability into the device driver. But that's not a big deal. So I think the other two are more important. I think we can kind of grow there, and then we can figure out the other one for ATS. Possibly the existing one itself is enough. Otherwise, we'll try to supplement it later, actually. That's good. Yep. Thanks, Jörg.
Okay.
It seems like you wrapped it up, Ashok. I don't know if there is anything else you want to discuss.
No, I think on this topic, I think that's pretty much what I had in mind, Lorenzo.
Thank you very much. Thank you, Jörg, as well. I mean, I think now we have a break, and we restarted 5 minutes past the hour. So thank you, and enjoy the break. Thank you very much.
You can hear me okay?
Yes,
I can hear you.
Yeah,
Great.
yeah. So, I mean, I think you should be all set up, and feel free to start anytime you wish.
Sure.
Thank you.
Okay. So I'm going to talk about. I'll set up some context first, but I'll be pretty quick about it. If anybody wants me to elaborate, let me know. I just think I'd like kind of most people will know kind of the area fairly well anyway. So what I'm hoping to do is for the IO virtual addresses. So for like finding free address ranges and allocating address ranges for like and assigning address ranges and freeing address ranges. We have a generic path for that, and we're hoping to replace the Intel's driver-specific version, the Intel's Iommu's driver-specific version of that with the generic code. And so there's a few issues. I've done this work, but there's a few issues that are preventing me from being able to merge it. So I was going to talk about those issues, and hopefully we can find some people who can help out with them. Just that it's the current issues are in GPU driver, and the code is fairly difficult to understand and fairly time-consuming to debug. So the generic path is in we call that the DMA-IOMU path. This is just a generic way of handling IO virtual addresses. Every driver pretty much had the same implementation for how they handle their IO virtual addresses anyway, so it kind of makes sense to have a generic path. I did the AMD conversion for that, so I removed the AMD specific way of handling the IO virtual addresses, and now it uses the DMA IMU path as well. Most, if not all, ARM CPUs I think use this path, but I'm not 100% sure on that. But just go to the next page. It's worth doing anyway. It removes a ton of code from the Intel IMU driver. And it just makes development so much easier if you're. It makes development a lot easier for everybody if we're all using the same path rather than having everybody rolling their own. So I'm going to talk about some of the issues. So the first kind of smaller minor issue is we need to port the Intel IMU implementation of how they do their bounce buffers. This is fairly recent code added. And we need to just port that over to the generic DMA IMU path. I think I can do this code mostly on my own, but it'd be good to get other people's inputs as well, just because I will only really be taking into consideration
how the Intel driver does it and what's useful for the Intel driver. So if other people, if this bounce buffer code that's in that patch there, if they think it would be useful for other drivers, they should definitely kind of give their input while I'm porting that code over. And another one that the code I don't really understand so much is the trace events for Iommu map and unmap in the Intel Iommu driver. This is just for tracing when map and unmap are called. I haven't ported that code over, and I don't think I really understand it well enough to port over. So it'd be great if I could get some help on that as well. But the bigger issue that's been preventing me from merging this for quite a while now is the way the i915 GPU driver ignores the return value of the map scatter-gather list. So this is when you have a scatter-gather list of various different allocated pages, and you want to map them with your IOMMU. Previously the Intel driver, you would send in the scatter-gather list, and each of the elements in the scatter-gather list would be mapped individually. But with the move to the generic path, the generic path uses the IOMMU to stitch together a bunch of those different elements, as many as it can, and so the output scatter-gather list will have like way fewer elements than the input list, and this is a change in behavior. And if the GPU driver obeyed the return value of map scatter-gather, this wouldn't cause any issues because this is part of the API. The return value of map scatter-gather will be the number of elements in the new list, but the i915 driver presumes that the number of elements in the output list will be the same as the number of elements in the input list, and so this causes issues.
Quick question. Isn't it the native, the normal IOMMU Intel driver also actually tries to merge the input list, right? So even though you might have multiple elements in the scatter-gather list, it's possible that you just get maybe one or maybe a few, depending upon how contiguous the IO virtual address allocation that we're able to get. I thought for that part it was the same. Like there was consolidation. It wasn't like a one-to-one actually for the map SG, I thought.
As far as I know, that's not the case. As far as I know, the output list that the Intel Iommu driver gives you has a one-to-one. The number of elements in the input list will be the same as the number of elements in the output list. That it doesn't stitch them together at all. I'll need to double check that. But I'm as far as I know, that's the case. If people are fairly sure that that's not the case, then there's probably a good chance that I've misunderstood something there. But
I think it might try to map everything into a single IOVA area, but then it still reports it as individual sections in the resulting list. That's probably what happens.
Right. Okay. Okay. In that case, the change in behavior then, the change in behavior in the DMA IMU path is that the list will be shorter anyway. The size of the list will be shorter. And that's causing this issue here where you get artifacts on the screen. So there's a few cases where it's clearly not obeying the kind of the return value of map scatter gather. That's for these two. Do you have a question, Georg?
So Robin, I have a question for Robin. So can we make this behavior of DMA IOMMU configurable so that we can switch it off for device driver that don't handle it well?
Yeah, I don't think there's any real reason we couldn't do that, especially now that Christoph's cleaned up a hell of a lot of the DMA API infrastructure anyway. We've already got things like the bypass flag, so I think it might be reasonable for a short-term solution just to add an additional don't merge scatter list segments flag. That's probably doable.
Yeah, okay. However we do it, I think the best would be a DMA API function like DMA map SKey handling broken or something, and print some warning message inside that the driver needs to be fixed, and let the driver who don't handle the map SG return very well call this function, and then the scatter merging will be disabled for them.
Well, come to think of it, you could even actually just use a DMA attribute on the DMA map SG call. That might.
Yeah, right. That's. But a warning would be cool somewhere to put pressure on the driver developers to get this fixed.
Yeah, ideally, that would definitely work as a short-term solution, and it would also mean that I could merge these changes, and I wouldn't have to keep rebasing them, which would be fantastic. I guess, yeah, ideally we would as well want a long-term solution where it just like obeys the API correctly. But yeah, if we're happy with that solution, then we can kind of go about implementing that as a short-term solution, and that would also mean that we get these changes merged, and then people could handle the issues in the I915 driver and other drivers kind of in their own time.
Yeah, that would be really, really great. I really like that all IOMMU drivers use DMA IOMMU. Robin recently sent a patch set to even converting the ARM 32-bit IOMMU drivers to use DMA IOMMU. So when these two things are done, then every IOMMU driver will use it, and that would be a big step forward, I think.
Fantastic. So in that case, then really we have a solution for this, which is where we'll do what you guys were saying, where it'll be configurable. And so that'll solve this issue in the short term anyway, and will mean that we can get this merged. Right, I guess so it would be...
The biggest amount of work is to make the bounce buffer implementation generic, but the other things should be solvable quickly, I think.
Yes, and even I did submit a patch there for the bounce buffer code with my previous when I submitted this previously. With so there is I do have that code there, and I've kind of checked it myself, but it really should be checked again. It was kind of I had to do it. It had just kind of this code had been merged during it was between two rebases that this kind of popped up. And it would be good for somebody else to check over that code. And also, if people think that they can benefit from this code, people thinking they can benefit from a generic bounce buffer, it would be good to get some other people's input as well. Now that we're doing it.
Yeah, I mean, going back to the previous discussion, I think we definitely want that certainly for ARM64 for untrusted devices, because that's the only way we can deal with that the same way as Intel does by using IOMMU DMA. So yeah, I think definitely we probably all want that hooked up sooner rather than later.
Great. I can link the patch that I've already submitted previously, and kind of get feedback on that. And then when the new patch set comes out, hopefully then I can address any comments.
Yeah, that'll be good. From what I remember, I do remember in the reviews that we kind of pushed it to being pretty generic already. So my impression is that hooking it up should be straightforward. So
it was pretty straightforward. The hooking up that I did, so straightforward that it kind of made me suspicious that I had missed quite a lot of stuff. So it was very generic. So hopefully it does just work. But again, it would be good to have somebody who just understands the area, especially for the ARM CPUs, to just kind of look over it.
Brilliant. So yeah, I guess that's probably going to be me. But yeah, so if you've got refresh patch series, then yeah, chuck it out, and we'll try and get a look.
I'm also missing the I'm missing the trace events as well. If somebody could, I'm not really sure what those are used for, or how they're used or anything like that. Is there anybody who would be available to look at that? So I haven't.
Are they for the actual DMA API calls? I think we have generic Iommu API trace events. I assume they're probably for the DMA stuff.
Right. I might have misunderstood that then. I know that okay, I'll need to look over those.
Yeah, so
those might not be an issue.
Probably we either add trace events in Iommu DMA itself, which is something that about once a year I kind of wish I had. Or possibly now that most of the actual core DMA API has been pulled out of line, it might be possible to actually install trace events at the very top level for that. So it applies to all DMA ops. That might be useful, although for the Iommu stuff we might want additional details specific to the mapping. So yeah, again, trace events in DMA Iommu should be entirely possible. You just need to remember how to.
Another thing I wanted to note as well is I no longer this is no longer my job to work on this code, which means that I'm kind of doing this in my free time, which limits the amount of time I can dedicate to it. If there's anybody else who who thinks that they would be a good fit for this, it would be much appreciated, especially if this is kind of, if anybody wants to see this stuff kind of as soon as possible. At the moment, I kind of have a lot on my plate already. But if nobody can take it on, I will kind of gradually get the patches out anyway.
Maybe the BTD maintainers can take responsibility of it when you post the next rebased version. Paolo, do you think you have cycles for that?
Yes, I can take this, thanks to Tom Murphy, and I can hand over the job.
That would be great. So yeah, I'll submit the next patch series, and then if somebody can take it after that, that'd be fantastic.
Okay, thank you.
Hi Tom, I've got a question. It's regarding this bounce buffer code. It looks like this seems to be very interesting work and which could be utilized for the networking part. Do we have any kind of, do you have any target? When would you like to complete this thing, the bounce buffer one, the link which you have showed him?
Sorry, could you repeat that last bit? Just the last few sentences there.
When you plan to complete this thing, or it's, it's still under process. What is the status of this particular work?
So just to be clear, I didn't write this code. I'll just be porting it over to the DMA IMU. I hope to have it as soon as possible, but again, I'm kind of very busy. This is really like kind of only in my spare time that I can really work on this. I can't really give any estimate for when it'll be done. And again, yeah, this isn't my patch.
Sure.
Also, just a quick note that the
networking driver. So this could be useful for various networking scenarios, like where the packets are small. So usually there is an overhead of the mapping and unmapping while you do the DMA, right? For the ones, it becomes even more if the size of the packet is small, right? So in certain cases, basically you would like to basically have, instead of doing normal, by going to the normal hardware SMMU or IMMU path, you would like to go through the software IoT LB path, which is like a bounce buffer, right? So
we tried the same. We also did the reverse. I think for the security, for the untrusted parts, if the buffer was fully page aligned, we tried to do the optimization. I think we didn't really get through with that because we didn't really quantify what the performance improvement was. But certainly for the small packet sizes, what you say makes sense. For things that are there, and that the IOMMU driver could automatically kind of implement the bounce buffering for those buffers, actually, where it's much smaller than a page size or something like that.
Yeah, exactly. So I was more interested in seeing its effect on, say, anything like, as you said, less than, say, even if it's a standard Ethernet size of 1.5K, that is 1500 bytes. So we have done a bit of an experiments at our own end, and then we could see that there's a lot of latency gain. So and of course, there's an increase in throughput as well, what you see for the small packet sizes. Maybe Robin could comment on this if there's anything we could add for the ARM64 specific thing, or we could take up this work for the ARM64 as well.
It certainly sounds like something we could explore. I mean, the main thing is just to get it working initially. Like I say, as far as I'm aware, the focus of the current implementation is just the security angle, but enabling it for performance cases, yeah, let's have a look at it.
I had the same thought, Robin, that Tom, that I think the idea was that when we use this bounce buffer for those little small packets, it'll be really helpful if we can relax the security on those ones, right? Just because the overhead of even doing a TLB flush is actually much more than the cost of mapping itself, actually, right? If we can get that same benefit by just not really doing the IOTLB flushing on the ones that we use the bounce buffer for, it'll help the performance much greater.
Okay. I might need some more details on that. I think I might need some more details on that just to implement that correctly.
I'll just add up one thing, the same thing like what Robin said, there is definitely a security angle to it. But then, I mean, these are the discussion what we would like to have in terms of can we do that kind of trade-off for, as what Raj said, that for the smaller packets if we are having some sort of gain in performance. So what is what is it, which way we should do the trade-off? Or can we actually do the trade-off? That's a more important question.
I think, well, it was a constructive discussion, guys. I think that thank you very much, Tom, for bringing this up and bringing it to something that looks like a successful completion. But unfortunately, I have to stop it here. Feel free to continue in NAC rooms and in the usual way. And thank you for presenting. Thank you.
Hi, everybody. Can you hear me?
Yes.
Perfect. Okay. So we have a device in recent Intel chipsets called the volume management device. A lot of people are familiar with it, but it's had some interesting challenges with it. What it is it's basically a PCIe to PCIe bridge. On the other side of that bridge is a new PCIe segment, mainly intended for NVMe devices with root ports and bridges and basically whatever else you can put on there that doesn't have I/O. So it has MMIO and prefetchable. It has similar rules to a PCI to PCI bridge. It's got a requester ID that changes to the VMD endpoint for anything behind it. But it also offers MSIX interrupts. So we have an MSIX table remapped into the VMD endpoints MSIX table. And there's an interrupt demultiplexer in the driver itself. So the VMD is, there's a couple on each server CPU, and in recent client CPUs are going to be moving forward with this product as well. The key point here is that with the requester ID changing to the VMD endpoint, the entire VMD domain, the endpoint and anything behind the VMD is in a singular IOMMU group. So we do get some pass-through benefits with this VMD model. We can pass through the endpoint itself and enumerate the domain in the guest. And what that allows you to get is some native hot plug support, and there's cross-OS RAID support with some of the Intel driver tools. It's very well aligned with some of the other OSs. We would really like to be able to support passing through individual sub-devices instead, or as well, rather. So passing through one of the NVMEs, we can, ignore passing through bridges and root ports. It doesn't make sense, but we would like to be able to pass through one NVMe or two NVMEs, different guests. We believe that there's going to be better hypervisor support if we do that, and also the OEM BIOS makers are pretty reluctant to add enable disable knobs. So this is something that we would like to just have them be able to do it. A couple of technical challenges that we've had. In the past, VMD, the driver itself, would indirect all the DMA ops to the endpoint. This was kind of a bad model because it wasn't using the device-specific configuration of an individual sub-device. Instead, it was using that device-specific configuration of the VMD endpoint. Prior to 5.6, the DMARC code would clear the entire SID's remapping context on the device removal. So that would be bad if we tried to remove one sub-device and another sub-device was still active. So we now support VMD sub-devices in the DMARC code. It keeps those SID-based contexts programmed until the parent device is removed, which typically only happens at shutdown or assignment. So I guess a couple of questions I have is that if we try to move forward with the sub-device guest pass-through, is it safe to hold DMA remapping contexts after sub-device removal, or is this something where we should be looking through and clearing the individual contexts instead? Anybody?
Yeah, I think holding it fast doesn't. I'm not sure if that is safe actually. But I like your last bullet. If you want to go through passive routing, that seems like a more safe, approach, and the Iommu also would support it. Not in current platforms, but in future ones where support scalable mode. So that is definitely something that I would be in favor of.
Okay. Yeah, I'll have to look more into that and how that will work out. Another challenge we have is due to the interrupt remapping. So the sub-device interrupt, if we were to assign the sub-device to a guest, unfortunately, the way the hardware works is that it would still dispatch the interrupt from the host's VMD. So the host VMD interrupt service routine would be unaware of the guest sub-device interrupt service routine because that driver is in the guest. So I came up with, a few ideas. One thing we can maybe do here is a Vfio ISR specifically for this kind of use case, and maybe that can be used to pass the interrupt from the host VMD driver to the guest.
John, just a quick question. So, these are independent MSI entries, correct?
Yes.
Why wouldn't doing posted interrupts for the guest actually work then? What is stopping that from working?
Well, the hardware itself is going to block and remap those entries into the host endpoint. So any MSIX that is received on the domain side, the segment side of the VMD on the outside of that is translated and resubmitted up to the root complex as if it came from VMD.
Okay, I don't understand the hardware aspects of how the VMD works actually, but it seems like that model is sort of suboptimal, given that if the delivery could be directly given to the guest, that is something that is a lot more efficient than hardware trying to do one more translation, giving it to the guest, and then the host actually, and then the host trying to actually do something, inject it back to the guest. It seems like a long path actually.
Yep. I agree. So some of the I sent out a patch set a few weeks ago to disable that remapping, but it's for specific hardware, and maybe we can combine that with PASID because it'll be in that time frame. So that might solve this technical challenge here if we don't have to add any of these specific hacks to get it going. That was it. Yep.
So both the DMA and the interrupt issues all kind of scream use an MDEV device. Is that what you're thinking relative to the VFIO?
So we could certainly do an MDEV device. That was kind of one of the options that was thrown out there. Are you thinking maybe like an MDEV NVMe device? Because that would make sense.
I would think it would be VMD specific, since it's going to have to pick out the right interrupt to send to the right device and use this PASID stuff. If there is a possibility that if there were NVMe devices exposed on the host, there have been various proposals of an MDEV NVMe driver, but those have largely been shot down as being non-performant and too complicated.
That was a concern. Okay. Anything else? All right. Thank you.
Thank you very much, John. Thank you very much. And I think, the next presentation is slotted at 40 minutes past the hour, so we'll give you, a short 5 minutes break, and then we restart with the last topic of the MC today. Hey, Kishan, I think well, you should be all set, and feel free to start anytime you wish. Thank you very much.
Okay. Okay, I think I can. I hope I'm audible. Okay, so I'll start. So this talk is about using Vfio transport for like two different systems. So one is for a system where a root complex and the PCI endpoint is connected, and both these devices run Linux. And the other type of system is like two different hosts are connected via an NTB, and these two hosts should be able to communicate using the Vfio transport. So the purpose of this talk is to provide an overview of the RFC series, which I sent some time back, basically to add support for Vfio-based communication and to really get feedback on any of the overall design aspects. Okay, so before starting getting into the details of how Vfio-based transport can be used, I'll explain how what is currently being supported. So for the root complex and endpoint connection, so there are like two SOCs here. SOC1 is connected to SOC2. SOC1 has root complex and SOC2 has endpoint. And both these SOCs run Linux. The endpoint in SOC2 is configured using the endpoint framework. So just to give a brief recap of how the endpoint framework looks like. So the bottom layer is the PCI endpoint controller drivers, and the top layer is the PCI endpoint function drivers. The middle layer is the core endpoint, which really abstracts the function drivers and the controller drivers so that any function driver can use any of these controller drivers. So there are a bunch of other controller drivers being added, which actually uses the endpoint framework, but there hasn't been any new function drivers added using the endpoint framework. So right now there is only this PCI EPF test function driver. During the last year's LPC, I proposed using creating an NTB function driver, but that only facilitates communication between two hosts, but does not really start or end the transaction. So which leaves with only PCI EPF test for doing any data transfers between the root complex and the endpoint. So the PCI endpoint test is the host side PCI driver corresponding to the PCI EPF test, which runs on the endpoint side, and the PCI test utility interfaces with the PCI endpoint test for performing the various for providing the various test functionality. So this performs tests like bar test, testing the various interrupts, data transfer tests like read, write, or copy, and for data transfer tests, it can also use DMA. So all this read, write, or copy can use only a single buffer. So while this scheme was helpful for really validating the communication between the root complex and the endpoint, this wasn't sufficient for implementing any actual use cases. So for actual use cases, it has to support multiple outstanding buffers, etc. And this also does not export any standard interfaces or does not provide any standard protocols for any of the standard applications to use. So one goal is to use a Vfio-based transport mechanism for communication between the SOC1 and SOC2, which is actually a connection between the root complex and the endpoint. And this is the second system. So here there are like two SOCs, SOC1 and SOC2, which are connected to each other using a non-transparent bridge. So here also both the SOCs run Linux. So the NTB software architecture looks something like this. The bottom is the NTB hardware drivers for supporting the various NTB hardwares. So the NTB hardware Intel supports Intel NTB device. The NTB hardware EPF actually is used to support an NTB which is actually configured using multiple PCI endpoint functions. So irrespective of this, the NTB really abstracts the various client drivers and the NTB hardware drivers. So the NTB tool, NTB perf, NTB ping pong are like small NTB client drivers, which are actually used for testing the communication between the two hosts. And NTB and NetDev is another client driver which actually provides an Ethernet interface for communication between these two hosts. So when you use NTB NetDev, any of the standard Ethernet applications could be used to for communication between these two hosts. However, for any other applications, a new NTB based client driver has to be developed. So here again, the goal is to avoid using NTB transport and use something like a generic Vfio based transport to leverage all the existing Vfio applications. So a brief introduction of Vfio. So Vfio is predominantly used in two places in kernel. It is used for communication between a host and the guest in the virtualization use cases. So the guest here will run Linux and use the Vfio infrastructure for any communication with the host, which actually runs the hypervisor. And it is also used for communication between different cores in an SoC. So an SoC could have like multiple cores. That could be one main A72 core, and that could be like other smaller Cortex R5 kind of cores. So the Linux running in the main core could actually use the Vfio infrastructure to communicate with the other smaller cores. So the Vfio has two parts. One is the front end, and the other is the back end. So the front end is actually whatever runs on in the guest VM, or it's like the Linux which actually runs in the main core, and Vfio backend runs in like hypervisor or other firmwares which runs in smaller cores. So the goal is to so here both the front end and the back end executes in the same system. So the goal is to separate this and make front end run in one system, which is like a root complex, and the back end in a different system, like the endpoint. And both these should be able to run Linux and should be able to communicate with each other. So for this terminology, I have also used vhost for referring the Vfio backend, mainly because the current Linux already supports some sort of Vfio backend, and these are implemented in the drivers vhost directory. So the Vfio by standalone, I would mean a Vfio front end, and vhost would mean a Vfio backend. So the advantage of using Vfio is it provides a standard producer consumer implementation. It can support multiple outstanding buffers. It can provide notification mechanism, and there are already multiple applications using the Vfio framework. So there is Vfio Net, there is Vfio RP message, which is typically used for communication between different cores. There is like Vfio SCSI and few other applications. So the Vfio front end and the back end will communicate using what is called as the Vfio ring. The Vfio ring will actually be physically present in the front end memory. So the Vfio ring will have so there are like at least two different layouts for this Vfio ring that is actually supported in kernel. The front end actually supports two different layouts, while the back end that is currently present, that is right now supported, has support for only one layout. Anyways, support for that could be added later, but for the initial RFC, I have used the only layout that is actually supported in the backend, which is the split V-ring layout. So this consists of a descriptor table, which really has a number of entries, which has addresses to the buffers, the length of the buffer, the flags which indicates readable or writable, and if it's the last buffer in the chain. The front end and the back end will so the front end back end will use this available ring and used tree to decide which of the buffers is available for it to actually transfer data with each other. So as I mentioned before, this Vfio ring is actually physically present only in the front-end memory. So the vhost or the Vfio backend should actually provide a mechanism to access the Vfio ring, which is actually present in the front-end memory. So it has to access the Vfio ring for getting the buffer addresses if it has to read or write data, or if it has to access the available ring to understand which buffers is available, and if it has consumed a buffer, it should update use ring. So the vhost should have the ability to actually update the Vfio ring. So the existing the current kernel supports two mechanisms for vhost to access the Vfio ring. One is if the Vfio ring is actually present in the user space buffer. So this is basically used for like KVM systems to access the KMU memory, and the other is providing and the other is the kernel right now provides supports for this Vfio ring, which is actually present in the kernel memory. So for the case where we have to use it for communication between root complex and endpoint, or for communication between two non-transparent bridges, we have to extend it to add support for memory mapped IO. So the vhost or the Vfio backend can access the Vfio ring using a memory mapped IOs. So the front end software is pretty much established. So the bottom layer, the Vfio PCI or the remote proc, actually registers the Vfio device. So while registering, it also gives an ID which actually determines which Vfio client driver can be used. So based on that, it will use either Vfio net or Vfio RP message. So the core Vfio layer really abstracts the Vfio function drivers with the actual drivers which actually creates the Vfio device. So by that mean, so by this abstraction, the Vfio net could be used either with Vfio PCIe or with the remote proc. So the Vfio PCI, when it actually registers the Vfio device, it will populate various config ops for the function drivers to utilize. So things like find VQs, delete VQs, get features, finalize features. So the Vfio PCI and remote proc actually populates these config ops, which could be actually used by these function drivers. So for instance, the find VQs will actually is a callback which actually creates the Vfio ring in the physical memory, whatever I just explained. So the get features callback will be used by the core Vfio to get the features of the Vfio backend. It negotiates, so the core Vfio will negotiate the features with the Vfio function drivers, and then communicate the negotiated features to the remote or to the Vfio backend. So there are other helpers like virtq add outbuff, add inbuff to actually populate the Vfio ring, and the virtq kick is actually send a notification to the Vfio backend. So in my proposal, what I'm actually trying to do is, so the Vfio front end is actually well established and it's already present in kernel. So in my proposal, I'm trying to create a symmetrical or parallel interface for the backend. So the current vhost or backend infrastructure does not provide the flexibility for it to be used with different types of devices. For example, the vhost net currently exists, but it always accesses Vfio ring, which is actually present only in the user space memory. So by having a proper framework, we could split so that the vhost net only provides provides an Ethernet interface, and the bottom layers can actually decide or actually access Vfio ring, which is actually present in different types of memory. It could be either memory mapped IO, or it could be in kernel, or it could be in user space. So here, for every entity on the front end, we have to provide a complementary entry in the backend. So for instance, the front end expects the backend to provide the number of buffers to be supported. So the backend interface should provide an interface for the vhost functions to provide the number of buffers that it requires. Similarly, the front end will require the set of features that is supported by the backend. So So the Vfio backend should provide provide the infrastructure to set the features. Similarly, it could set some status, and the backend could handle the status correspondingly. So for each entity here, there should be a corresponding entity on the backend. So here the vhost PCI EPF will communicate with Vfio PCI EPF. The vhost NTP will communicate with Vfio NTP. Similarly, on the upper layers, the Vfio net and vhost net are similar. Can communicate with each other, and similarly, the Vfio RP message and vhost RP message are like parallel interfaces. So the vhost backend will provide a service to the front end. So the first problem is to, yeah, sure.
Just a quick interjection. Are you proposing here to introduce a new Vfio transport with its associated configuration and notification mechanism? So something that basically stands beside Vfio PCI and Vfio MMU and Vfio CCW, for example.
So whatever you're asking is actually on the front end. So the front end, I'm not actually creating any parallel interface, though I'm creating an interface that is similar to Vfio PCIe. So for example, the Vfio PCI and Vfio PCI EPF are a lot similar. The Vfio PCI EPF will actually interact with the vhost PCI EPF. So that's because the Vfio PCI actually supports two types of interfaces, right? One is a modern interface and one is the legacy interface. But when we use something like a vhost PCI EPF, which is like an actual hardware that is running on the back end, there are the existing the legacy or modern interfaces cannot be used. So that's the reason we introduce a new driver for communicating with the backend. So similarly, when you use the non-transparent bridge, so there is really no Vfio interface for communicating with the non-transparent bridge, right? So here the Vfio NTP interacts with the NTP framework to provide a Vfio interface. So the Vfio NTP will create a Vfio device so that the Vfio net can either use one of these, can use the Vfio device created by one of these interfaces.
Yes, so that really sounds to me like you are introducing a new transport, which is obviously completely fine. If I take the usual Vfio terminology, you have the device and you have the driver, and they need to communicate on some kind of level. So you want to use something that is different from Vfio PCI because you have different things you needed to do. I think you should really think of it not as a Vfio PCI variant, but something completely different, which basically is using the same interfaces that the other transports do. I hope you understand what I mean.
Okay, so your point is both the PCI EPF uses the Linux PCI core and the Vfio PCI uses the Linux PCI core, because both these are like PCI drivers. So your point is, instead of using a PCI driver, I should try to use something else.
No, but PCI is fine using a PCI backend. It's basically what I think you need, if I understand you correctly, is a different communication mechanism between the two halves of what you call the front end and the back end.
Correct, yes.
So this is what the standard, for example, is calling a transport. I think that is what you want, but this really sounds like something which should probably be discussed on the Linux virtualization list, because there are also the Vfio experts hanging out there.
Okay, so I'll just quickly skip these slides, and so these are like helpers which actually provides us to access the mechanism. So Jian Wang, who is one of the Vfio maintainers, provided an alternate approach during one of the reviews. So his point was, instead of creating a parallel vhost infrastructure, his point was to use the Vfio front end on both the sides, but use an adapter layer, right? So which has like two vhost interfaces. So the one vhost will interface with the Vfio front end, and the other vhost interfaces with the Vfio backend, and it provides like an adapter layer for communication between the two ends.
Kishan, I need to stop you here. Unfortunately, I don't know if well you.
Thank you.